Your heart doesn't beat in seconds. It beats in spikes, millisecond jolts of electricity. Your eyes don't see in minutes. They sample reality in blinks. Even your decisions, those moments you swear took forever, often crystallize in a few hundred milliseconds. Now imagine the universe doing the same thing, compressing the power of a star into the length of a blink, and flicking it across billions of light years straight into our antennas. When we catch a sharp, repeating flash from deep space, how do we know if it's a message, or a natural disaster? If the universe can produce a perfect millisecond note, is it singing, or just cracking? I'm Rowan K. Mercer, and this is the Science Audit. Tonight I want you to come with me into a very specific kind of darkness, the kind that isn't just night, but radio night, where the sky becomes a vast ocean of static, and we listen for the briefest ripples. Because fast radio bursts, FRBs, are not just another weird astronomy headline. They're a stress test for how we infer truth when nature behaves like an intelligent signal. They're a lesson in humility. And if we learn to read them correctly, they might become one of the most powerful tools we've ever built for mapping the invisible universe. So let's put ourselves at the console. You're in a control room that smells faintly of warm electronics and stale coffee. A wall clock ticks like it's mocking you, because the event you're waiting for won't even last long enough for the second hand to twitch. On the monitor is something that looks almost disappointingly ordinary: noise. Random fuzz. A storm of radio static from a cosmos full of charged particles, exploding stars, rotating neutron spheres, and human-made interference leaking into the sky. And then there, a needle through the storm. A bright, clean spike. A flash. Gone. It's not a star you're looking at. It's not a galaxy in a pretty picture. It's a timestamp wound in your data, a burst of radio energy arriving in a millisecond. And if you do the naive math, if you assume it radiated in all directions, and you use the distance implied by how the signal has been stretched and delayed, you get a result that makes your stomach drop. Something, somewhere, just did something violent enough that, for an instant, it outshone entire galaxies in radio light. But here's the thing that turns this from cool into existential. The signal is structured. It has shape. Sometimes it repeats. Sometimes it arrives with patterns, activity windows, quiet seasons, bursts within bursts. Sometimes it's polarized, like it passed through a magnetic labyrinth. In other words, it behaves the way we expect nature to behave when it's complicated, and also the way we would design a beacon to behave if we wanted attention. So we need a lens, a principle, a way to keep ourselves honest. Think of it like this: you're standing outside in a snowstorm at night. Every streetlight has a halo. Every car headlamp becomes a smeared comet. Your brain starts inventing shapes in the blur, faces, letters, intentions. The light is real, but the story you're tempted to assign to it might not be. That's what FRBs are like. There is a sharp light. There is a stormy medium. The entire challenge is separating what the source is doing from what the universe is doing to the signal on the way to us. So first we build the basic map. What are fast radio bursts really? How do we detect them? And why does the mainstream explanation, Magnetars, fit so well that it's both comforting and unsettling? Then we walk right up to the edge. The paradoxes, the repeaters, the cycles, the polarization so extreme it feels like the cosmos is twisting the dial in real time. And finally we do what the Science Audit always does. We ask what this mystery teaches us about reality, and about the kind of minds we are, staring into noise and praying for meaning. Alright. Faster tempo now. Let's define the object of our obsession. A fast radio burst is exactly what it sounds like. A burst, fast, of radio waves. Milliseconds long. The part that's easy to say and hard to feel is where they come from. Many are extragalactic. Not across the Milky Way, but across the gulf between galaxies. That means by the time their radio waves reach Earth, they've traveled for hundreds of millions, sometimes billions, of years. FRBs were first found in a way that feels almost like a parable about modern science. Not by a grand planned discovery, but by someone digging through old data. Archival recordings from pulsar surveys, projects designed to find spinning neutron stars, contained an anomaly. A pulse too short, too bright, too dispersed to be a known pulsar. It was like searching for seashells and finding a bullet. Now, how do you even detect a millisecond event from another galaxy? You don't see it like a picture. You measure intensity, radio brightness, over time and frequency. Imagine a piano roll, but instead of notes, It's radio power, and instead of music, it's the universe whispering in static. The telescope records a waterfall plot, time on one axis, frequency on the other, brightness as color. And here's where the first crucial idea enters: dispersion measure. I want you to hold this metaphor tightly, because it's the reason we know FRBs are so far away. Space is not empty. It's filled with a thin mist of free electrons, charged particles drifting between stars and galaxies. When a radio wave travels through that electron sea, the lower frequencies get delayed more than the higher frequencies. It's not because the wave slows down, like a car hitting traffic. It's more like a runner trying to sprint through deep snow. The lower frequency part plows more, loses time, arrives later. So the burst that left the source at once arrives at Earth smeared into a downward sweep, a cosmic delay line. That smear can be measured. And the amount of smear, the dispersion measure, the dm, tells you how many electrons the signal encountered along its path. If the dm is too large to be explained by the Milky Way alone, then the source must be beyond it. That's one of the first gut punch moments in FRB science. The universe itself signs the signal with a distance clue. But there's a second concept that really makes your intuition wobble: brightness temperature. This is physics' way of saying, if this were ordinary thermal glow, like hot metal or a campfire, the implied temperature would be absurd. Impossible. It's not actually that the source is that many degrees Kelvin. It's that the intensity is so concentrated in time and space that, if it were thermal, it would require unphysical heat. So the emission must be coherent. Coherent means the waves are marching together. Like a laser instead of a light bulb. A campfire throws photons in chaotic independence. A laser is an army in step. FRBs look like an army in step. And that immediately tells you, whatever is making them is not just hot. It's organized, at least at the level of electromagnetic phase. Now here's a question that should already be forming in your mind. If we know the burst is dispersed and smeared by electrons, how do we know what the original flash looked like? We don't, at first. We mathematically dedisperse it. We reverse the delay, sliding the lower frequencies back in time until the burst lines up into its sharpest possible spike. And when it clicks into focus, it feels like turning a radio dial and suddenly hearing a voice emerge from static. The early era of FRBs was like hearing that voice once, then never again. One-off bursts. That made theorists reach for catastrophic events, things that happen once: a neutron star collapsing, a merger, an explosion that ends an object's life. But the universe, as usual, refused to cooperate with our neat categories. Because then we found repeaters. Not just one. Many. Sources that burst again and again, sometimes with clusters of activity like thunderstorms, sometimes with long quiet gaps like seasons. And that single fact, repetition, changes the entire emotional texture of the mystery. A one-off could be a death scream. A repeater feels like a machine, or an engine, still alive. So we needed better instruments, better localization. Early detections could tell you, somewhere in this patch of sky. But that patch might contain thousands of galaxies. To identify a host galaxy, you need to pinpoint the FRB's origin far more precisely. This is where interferometry becomes a kind of scientific superpower. Instead of one dish, you use many antennas spread out over distance. You combine their signals, and the pattern of arrival times lets you triangulate the source with exquisite precision. It's like turning several blurry eyes into one sharp gaze. With that, we began to link FRBs to actual galaxies, dwarf galaxies, spiral galaxies, old stellar populations, star-forming regions. The diversity itself was a clue. Whatever makes FRBs might not need a single special kind of home. Now we come to the leading engine, the mainstream contender that, right now, explains more than anything else without forcing the universe to do backflips: magnetars. Picture a star more massive than our sun dying. Its core collapses. Protons and electrons get crushed together into neutrons. The result is a neutron star, a city-sized sphere, around 20 kilometers across, with more mass than the sun. It's like packing a mountain into a sugar cube, and then letting it spin. Neutron stars already feel like science fiction, but magnetars are the ones that make even astrophysicists speak a little more quietly. A magnetar is a neutron star with a magnetic field so intense it's hard to express without losing the emotional meaning in the zeros. Trillions of times stronger than Earth's field. Strong enough that, in the magnetar's neighborhood, atoms don't behave like atoms anymore. They stretch. They distort. The vacuum itself becomes a kind of optical material. Light can split into different polarizations just by traveling through empty space near the star. So how does a magnetar make an FRB? The story we tell, always provisional, always under audit, goes like this. A magnetar's crust is not a gentle shell. It's an ultra-dense lattice under unimaginable stress. Magnetic forces twist it. Eventually, it cracks, a stark wake. That crack rearranges the magnetosphere, the magnetic environment around the star. Field lines snap and reconnect, like solar flares on steroids. Charged particles get accelerated. Coherent radio emission can be produced in that violent electromagnetic choreography. And magnetars don't just exist in theory. We've observed them in our own galaxy. We've watched them flare in X-rays and gamma rays. We've seen their tantrums. And in 2020, something happened that made the magnetar case feel dramatically more grounded. A galactic magnetar named SGR 1935+2154 produced a burst of radio energy that looked scaled down in power because it was close, eerily like an FRB. It was like the universe handing us a local laboratory version of a phenomenon we'd only seen from afar. Not perfect, not definitive, but persuasive. The kind of event that makes a room full of skeptics stop tapping their pens. Magnetars fit other constraints too. Millisecond timescales? A neutron star's environment naturally operates fast. Extreme energy? Yes. Episodic activity? Absolutely, magnetars flare unpredictably. Repetition? They can do it. And some FRBs are associated with star-forming regions where magnetars could plausibly be born from massive stars. So is that it then? Mystery solved? Here's where the snowstorm returns. Even if magnetars are the engines, what we detect is not the engine alone. The signal travels through the source's local environment, maybe a supernova remnant, maybe a nebula, maybe a dense star-forming region. It then crosses the intergalactic medium, a thin, structured web of plasma. Then it enters our galaxy's own electron fog. And along the way, the burst can be reshaped. This is why propagation effects matter so much. Scintillation is like twinkling, but for radio. It's the signal flickering as it passes through turbulent plasma, like starlight shimmering through Earth's atmosphere, except the air is ionized gas spread across light years. Scattering can smear the burst, stretching it, adding tails. Plasma lensing can focus or defocus it, like invisible magnifying glass pockets drifting in space. A burst can be amplified, split, distorted. Imagine holiday lights seen through falling snow. The bulbs are fixed, but the snow makes them dance. That's the medium. That's our problem. Now let's slow down. Because once you know enough to feel magnetars as plausible, you also know enough to feel the edges where the story frays. The first edge is the too bright, too fast problem. Coherent emission at these distances demands extreme conditions. It's not just a lot of energy. It's energy channeled with precision into radio waves, released in milliseconds, and not immediately absorbed by the surrounding plasma. Many emission mechanisms can be written down on paper, but nature has to actually run them without self-destructing the signal at birth. So you start asking questions that feel less like astronomy and more like interrogating reality itself. How can something be so coherent yet so messy from burst to burst? Why do bursts from the same source look like different dialects of the same language, sometimes narrowband, sometimes broadband, sometimes with multiple components, sometimes with intricate sub-millisecond structure? And then there's the split personality of the population. Repeaters and apparent one-offs. Are they truly different kinds of objects? Or is repetition partly an illusion of our limited observation time, like declaring a volcano inactive because you only watched it for an afternoon? Or could it be the same underlying engine, but the medium acts like a gate, sometimes letting bursts through, sometimes hiding them? Consider this: if a source emits bursts often, but most of them are too faint for us to detect, we would only see it repeat when conditions are favorable, when plasma lensing boosts it, when scattering is low, when our telescopes happen to be looking. So the line between one-off and repeater may not be a clean biological taxonomy. It might be observational weather. Now we add another axis of strangeness: polarization. Polarization is the orientation of the radio wave's electric field, like the direction a jump rope is being shaken. Some FRBs are highly polarized, which already hints at coherent processes and ordered magnetic fields. But the real tell is rotation measure. Rotation measure is what happens when polarized radio waves pass through magnetized plasma. The polarization angle rotates, and the amount of rotation depends on electron density and magnetic field along the line of sight. So a huge rotation measure means the burst passed through an environment with intense magnetization and plasma density. Some FRBs show rotation measures so extreme that the natural picture becomes, this source lives in a magnetic furnace. And now, this part matters for the emotional arc, periodicity enters the chat. Some repeating FRBs don't just burst randomly. They have activity windows. 16 days in one famous case, a cycle where the source is active for a few days and quiet for the rest. If you're human, your pattern-hungry brain instantly wants to leap. A schedule. A lighthouse. A transmitter. And yes, if you were designing a beacon, you might choose a regular cadence to make it stand out. But nature loves cadence too. Orbiting systems have periods. Precession, like a spinning top wobbling, has periods. Magnetospheres can have cycles. Even accretion, the flow of matter onto compact objects, can turn on and off with rhythm. Periodicity is not a fingerprint of engineering. It's a fingerprint of dynamics. So here's a thought experiment, and I want you to actually live inside it for a moment. You're not an astronomer. You're an alien engineer. You want to be noticed across the galaxy. You have constraints, energy cost, pointing accuracy, the need to pierce plasma. Would you broadcast a continuous message? Probably not. That's expensive. Would you send narrow band tones like a pure whistle? Maybe, because narrow band stands out from natural broadband noise. Would you modulate in a way that screams, math? Possibly prime numbers, repeating sequences, structured encoding. Now look at many FRBs. They are often broadband. They are often messy. They drift in frequency. They show scattering and lensing. They have burst-to-burst variability that feels more like weather than language. Not impossible for engineering, but not what you choose if your goal was unambiguous recognition. And here's the discipline: extraordinary claims require multiple independent lines of evidence. Not just, it's weird. Weird is common in astrophysics. We would want sky position stability at extreme precision. We would want narrowband features that don't look like plasma effects. We would want engineered modulation, information-bearing structure that survives propagation and repeats in a way that can't be mimicked by turbulence. We'd want energy budgets that make sense for technology. We'd want multi-wavelength counterparts that align with a plausible artificial system. And crucially, we'd want reproducibility. Patterns that hold up when the sample size grows. Science is not the art of being cynical. It's the art of not being fooled by our own yearning. So we keep Magnetars on the table, strongly. But we also keep the door open to the fact that we might be missing pieces. This is where the frontier speculation appears, and I want to handle it carefully, the way you handle a powerful chemical in a lab. With respect, not fear. There are models involving exotic compact objects, things like cosmic string cusps or other hypothetical relics. There are ideas involving axion-like particles, ultralight fields that could convert into photons in magnetic environments, creating signals that might mimic bursts. There are gravitational lensing echoes, where a burst takes multiple paths around a massive object, arriving in repeated copies separated by milliseconds to days. These are not fantasies. They are proposals. But proposals aren't equal. A good model doesn't just explain what we already saw. It predicts something specific we can test. A smoking gun is not. It could fit. A smoking gun is. It must produce this signature, and if we don't see it, it dies. So what would count? For lensing echoes, repeated burst copies with identical internal structure but delayed in time, matching lensing geometry. For axion-like conversion, correlations with magnetic environments, and spectral features consistent with conversion physics. For exotic compact objects, event rate distributions, energy scaling, and spatial correlations that can't be matched by neutron star populations. That's the difference between wonder and discipline. Now let's come back to the deepest paradox question, because I think it's the one that changes you as a thinker, not just as a science fan. Are we seeing the source, or mostly the medium between us and the source? There's a humbling possibility that the most important thing FRBs will teach us is not what makes them, but what they illuminate. A lighthouse is valuable not only because it exists, but because it reveals the shape of the coastline. And that brings us to the philosophical payoff, without leaving the physics. FRBs are cosmic flashlights. Every burst carries an imprint of every electron it passed. That means we can use dispersion to weigh the invisible matter between galaxies, the missing baryons. This missing baryons problem is one of those quietly radical facts about cosmology. We can predict, from the early universe and from nucleosynthesis, how much normal matter, protons, neutrons, the stuff of atoms, should exist. But when we count it in stars and gas, a lot seems unaccounted for. It's not dark matter, it's ordinary matter hiding in diffuse, hot plasma in the cosmic web. FRBs, because they're bright and short, act like needles we can thread through that web. Each DM measurement is like a core sample taken through intergalactic space. With enough FRBs, you can map where the missing matter lives. And polarization gives us another map: magnetic fields. The universe is magnetized in ways we don't fully understand: how fields seed, grow, and shape galaxy formation. Rotation measures from FRBs can trace magnetism across galaxies and clusters. They can tell us whether magnetic fields are primordial whispers from the early cosmos or products of astrophysical dynamos. Even scattering and lensing, the distortions that frustrate us, become tools. If bursts are delayed, smeared, or split, that tells us about turbulence and structure in plasma. In some cases, lensing could probe compact dark structures, small-scale clumps that other methods miss. So the same phenomenon that tempts us into myth becomes an instrument for measurement. And that is a recurring theme in science. The universe hands us a mystery, and when we finally understand it, it turns out to be a ruler. But there's a deeper lesson that lives underneath all the data plots. Science is not just discovering facts. It's building a way of thinking that resists our most seductive errors. Our brains are meaning machines. We see faces in clouds. We hear messages in static. We look at a repeating signal and feel the ancient pull: someone is calling. That pull is not shameful. It's human. It's the same instinct that makes us bond, that makes us create language, that makes us survive. But the discipline, the beauty, of science is that we don't punish the instinct. We harness it. We take the story our minds want to tell, and then we build tests sharp enough to cut through it. We ask, what else could cause this? What prediction distinguishes them? What observation would change my mind? So let's return, one last time, to that snowy night image. You're outside, watching distant lights through falling snow. Your brain wants to see a pattern. The lights blur and shimmer and dance. You could decide it's a secret code, or you could measure the snow, the wind, the optics, and learn how the world bends light. Either way, you feel something: the ache of not knowing, and the thrill of maybe knowing. Now, uplift, forward momentum, because the next decade is where this story becomes something else. We're moving into an era of larger surveys and real-time localization. Instruments like CHIME open the floodgates by catching huge numbers of bursts. Arrays and networks are getting faster at pinpointing positions quickly enough to trigger follow-up across the electromagnetic spectrum: X-ray, optical, gamma. Multi-messenger astronomy, too. If an FRB ever coincides with a gravitational wave event or a neutrino burst, that would snap whole branches of theory into place. We'll find more repeaters. We'll characterize their environments. We'll watch their cycles evolve. We'll learn whether one-offs are truly singular or simply shy. And gradually the question will shift from, what are FRBs? to, how do we use FRBs? But let's not rush past the synthesis, because you and I started with a human question, and we owe it a human answer. Here's what we've learned. Fast radio bursts are millisecond flashes of coherent radio energy, often from far beyond our galaxy. Their signals are shaped by a universe filled with electrons and magnetic fields, leaving measurable fingerprints, dispersion and polarization, that let us infer distance and environment. Magnetars, ultra-magnetized neutron stars, fit many of the facts: extreme fields, fast timescales, episodic repetition, and at least one striking galactic analog. Yet the details remain sharp enough to cut: the variability, the polarization extremes, the periodic windows, the messy substructure. Some of what we think we see may be the source. Some may be the medium. And our job is to separate song from cracking. Now a contemplative takeaway, something you can carry into your own life, not just into a comment section. Imagine that every conversation you've ever had is an FRB. A brief burst from one mind to another. And between you and the other person is a medium: history, mood, stress, culture, trauma, love. The message leaves the source clean and arrives smeared. How often do we judge the sender for what the medium did to the signal? And now the next great question, the one that keeps the door open. If nature can produce signals that feel almost intentional, what does that say about our confidence in recognizing intention when it's real? If time is compressed into millisecond notes across billions of years, what else is the universe doing right now, quietly, coherently, that we're still calling noise? Maybe FRBs aren't the universe speaking to us. Maybe they're the universe teaching us how to listen. If you want to keep going, click the video on your end screen. Don't stop the session here, because what comes next connects directly to this question of signal versus storm. And if you're new to the Science Audit, subscribe, not for certainty, but for the habit of careful wonder, the kind that changes your mind with evidence and keeps your awe intact. One question for you, and it's easy when you hear repeating bursts with periodic windows. What's your first instinct, natural engine or intentional beacon? Answer with one word, and tell me why in a sentence.